Hi everyone, today we'll start our discussion on transients in power systems and our first topic is lightning. Lightning is the most common cause of outages in overhead lines, both in transmission systems and distribution systems. When lightning strikes an overhead line or a tower, it injects a large magnitude pulse of current into the system. This pulse of current will start traveling along the lines in the form of a traveling wave, and on its way it'll create overvoltages in any equipment that is there. So it's likely to create a lot of damages to the system if not mitigated correctly. There are different types of lightning. These are classified based on the type of electric charge of the lightning, as well as where it's initiated. So a lightning can be negatively charged or positively charged, and also it can start from the cloud towards the ground or the other way around. Start from the ground and go towards the cloud. Out of these four different categories that I'm showing here, the negative cloud to ground lightning is the most common type. And this is the one that we're going to be talking about for the rest of this lecture. All right, let's consider the most common type, negatively charged cloud to ground lightning. In order for this lightning to form, there are multiple steps. The first step is charge separation within the clouds. This process is not entirely known. There are different theories about how this happens. One is that water droplets, as they move towards the bottom of the cloud, they attract negative charges and bring them with them to the bottom, leaving some positive charges at the top. Another theory is that as water droplets are moving towards the bottom of the cloud, they collide with the moisture that is rising. As a result of this collision, electrons are going to be released and they will be gathering at the bottom of the cloud. Regardless of the theory, what happens at the end is you're going to have a section of negative charges and a section of positive charges, as you can see in this diagram. As a result of the negative charge accumulation at the bottom layer of the cloud, we're going to have positive charge accumulation at the surface of the ground, right underneath the cloud, and this will create an electric field. The next step is the formation of the leader. This is a process that starts from within the cloud. If the voltage gradient inside the cloud exceeds the breakdown strength of the humid air inside, it will create an ionized path through which the negative charges will start moving towards the bottom of the cloud. So it starts from somewhere like here and moves towards the bottom of the cloud, and then when it gets there, it sticks out of the cloud. This is what we call a leader. A leader moves downwards towards the ground. However, it doesn't necessarily do this in a straight line. Instead, it has some sort of a zigzag pattern to it, as you can see in this diagram. The reason for having that zigzag shape is that the strength or dielectric strength of the air in that vicinity is not necessarily uniform in all directions. If in some direction you have more impurities or dust or water droplets or things like that, the air will break down more easily in that direction and the leader will move along that particular direction. The next step is the rise of a streamer. Streamer is pretty much the same concept, except that it has a different type of charge. So when you're talking about negatively charged cloud to ground lightning, the leader is going to be negatively charged and the streamer is going to be positively charged. And similar to leader, it creates that ionized path and it tries to rise towards the cloud. The last step is when the leader and the streamer basically meet. When they meet, they create a channel through which the positive and negative charges neutralize one another. This is what we call a return stroke. Typically, you have more than one stroke. So every lightning flash can consist from anywhere from a couple of strokes up to like 30 or 40 strokes. Each stroke lasts about 100 microseconds, and the current that flows through it is extremely large, about 20 or 30 kiloamps. This energy that is released as a result of neutralization of the positive and negative charges, it basically heats up the air in that channel so much and so rapidly that the air explodes. And this is basically what we hear as thunder. Now, when you design a power system, you have to take into account the lightning activity in that particular geographical region. This comes into play, for example, when you want to decide on having guard wires or the number and locations of surge arresters, or perhaps the ground impedance that you want to have for your towers and poles. So it's an important metric. We have different ways to quantify lightning activity in a geographical region. One is the notion of thunderstorm day. Thunderstorm day is a 24-hour period in which at least one thunder is heard. And we then develop maps that are called isochronic maps that show equi-thunderstorm contours. So each contour would be geographical areas that have the same number of thunderstorm days per year. This is a metric which is quite straightforward. However, it has some deficiencies. One is that it does not distinguish between cloud-to-cloud lightning and cloud-to-ground lightning. For power system purposes, cloud-to-ground lightning is a lot more important and critical than cloud-to-cloud, whereas this metric doesn't distinguish between the two. The other issue is that as long as you hear at least one thunder, you count that as a thunderstorm day. So again, this metric doesn't distinguish between a day in which, for example, you have 20 lightnings and a day where you have only one lightning. However, as you can imagine from a power system perspective, these are two very different situations, which are not really being reflected well in this particular metric. Another metric that we can use is ground flash density, or GFD. GFD tells you the average number of lightning strokes that occur per unit area per unit time for a particular location. The units of GFD are number of flashes per kilometer squared per year. What we do is we install different types of lightning location systems and flash counting systems that, in addition to recording the exact event of lightning, they can even record other useful information, for example, the exact date, the exact time, the location, the number of strokes that took place in that particular lightning flash, and even estimates of what the peak current was and what its polarity was, for example, negatively charged or positive charged. This is a very, very useful information for power utilities in order to decide what type of mitigation techniques they have to have in place. This is something that we'll discuss in our future lectures. When GFD data is not available, there are empirical equations that allow you to estimate those using thunderstorm days. One is that GFD is 0.04 times number of thunderstorm days per year to the power of 1.25. If you have number of thunderstorm hours per year, then it would be to the power of 1.1. If you don't have GFD data, you can use this approximation to have an estimate for it. Now, as I mentioned at the beginning of this lecture, when lightning strikes a tower or an overhead line, it injects a current pulse into the system that moves along the overhead lines in the form of a traveling waveform. This pulse of current is unipolar. It's either positive, reaches a peak and then decays down, or is negative. This is unlike other types of transients that we'll be talking about in this course later on. For example, switching transients that are oscillations that will go positive and negative. So lightning, remember, that is unipolar. Depending on the charge, it's either positive or negative. It typically rises to its peak within a few microseconds, and usually within 100, at most 100 microseconds, it reaches half of its peak value. That means it decays to that value. The peak of the current really depends on the type of the lightning. For this particular negatively charged cloud to ground lightning that we're mostly concerned with, the peak of the current can reach even up to 100-150 kiloamps. This diagram shows the frequency of occurrence of various current peaks based on historical data. So you can see that for 50% of the cases, you expect to get a peak current of 40 kiloamps or less. And there's only 10% of the cases in which the current can exceed 80 kiloamps and higher. Now, in order for us to test equipment in the lab, we have to simulate a lightning waveform. IEC has standardized this waveform, and this is known as 1.2/50 microsecond. And I want you to remember this because this is a very, very important waveform. The first number is the rise time. The rise time is defined as 1.67 times the interval between 30% of the peak and 90% of the peak. So as I mentioned earlier, the waveform goes to a peak and then decays down. And if this is the peak value, this would be the time to 30% of the peak, and this is the time that it takes to 90% of the peak. So this duration from here to here, you multiply it by 1.67, and that is your rise time. And then the second number, the 50 microseconds, that's the tail time or the decay time. That's basically the time it takes for the lightning to drop, the lightning current to drop to 50% of its peak value. So if this is the 50% peak value, this will be your tail time or the decay time. So the standard waveform by IEC is 1.2 microsecond / 50 microsecond. That means it takes 1.2 microseconds to rise and then 50 microseconds to decay. Mathematically, you can model it as this function E of t, which has an E of p, which is the peak current, times e to the power of minus alpha t minus e to the power of minus beta t. And again, for 1.2/50 microsecond waveform, these are the values for alpha and beta. So this is the waveform that we generate in high voltage labs in order to test equipment. The one thing that you have to keep in mind though, for the actual lightning, it's possible to have a much quicker rise time, and it's also possible for the lightning to have longer durations. So if an equipment passes the insulation test for 1.2/50 microsecond waveform, that does not give us any guarantee that that equipment can withstand any actual lightning in the field. It is possible that it is exposed to a lightning that either has, shorter rise time or a longer decay time, and an equipment that has passed in the lab might fail out in the field. So that's something you have to keep in mind. Now, there are different scenarios through which lightning can induce transients in the power systems. These would be if lightning strikes a tower directly or the shield wire on top of the tower, or if the lightning hits one of the phase conductors, or if it hits the ground next to the tower, and finally, if we have cloud-to-cloud lightning. And we'll see through the next few slides what the effects of each of these scenarios will be. So let's talk about the first one. When the lightning directly strikes either the tower or the ground wire. When this happens, and imagine this is the lightning, so you have a current in the form of a pulse, let's say something like this, that is moving towards the tower itself. Imagine I have a guard wire here, so if I write the KCL at this particular node, the incoming current, which is the lightning current, will be split into three portions. One would be the portion that will go through the tower to ground. The other portion is that traveling wave that travels along the ground wire in this diagram to the right, and the other portion is the traveling wave that travels along the ground wire to the left. And of course, as you probably recall from power system analysis, every time that this traveling wave hits a particular joint, like two conductors, for example, that have different characteristic impedances, or for example, even a tower along the way, part of it is going to be reflected, part of it is going to be refracted. So the actual picture is a lot more complicated than this. We're going to have multiple versions of these traveling waves getting reflected, refracted, that you can calculate using Bewley lattice diagram. All right, let's do an activity here. So imagine that I have this overhead line structure with towers that have ground wires or shield wires. The shield wire has a characteristic impedance of Z of shield, and the tower has a resistance of R of tower. I have a lightning strike that hits this particular tower and the shield wire, and as we saw before, the current is going to be split. Part of it is going to go through the ground wire, part of it is going to go through the tower to ground. What I would like you to do is to find an equation for the voltage that is dropped across the tower itself as a function of the current of the lightning. So at this point, I'd like to ask you to pause the video, give yourself a few minutes, just think about the KCL equation that I mentioned on the previous slide, write it down, and see how you can relate these two variables to one another. All right, assuming that you wrote the KCL at this point, you probably got to something like this. Your incoming current, which is I of stroke, will be one portion that will go here, another portion that will go here, another portion that will go here. The current that will go through the tower, if I call the voltage drop along the tower to be V of tower, that current will be V of tower divided by R of tower. The current, the portion of the current that will flow along the ground wire to the right will be V of tower, the voltage dropped along the tower, divided by the characteristic impedance of the shield wire. And the portion that will go to the left will be the exact same value. Again, V of tower divided by characteristic impedance of the shield wire. So this portion plus this portion will be 2 times V of tower divided by Z of shield. And if I rewrite that equation, basically write V of tower as a function of lightning current, V of tower will be I of stroke times this portion, Z of shield divided by 2 plus Z of shield divided by R of tower. Now, let's think about this parameter R of tower. That's the resistance of the tower. If this value is large, if this is a large value, this portion will be small, meaning that this entire value is going to be large, meaning that you will have more voltage dropped along the tower. What is the problem with that? This voltage might be so high that might break down the insulators. So one of the ways to make sure that you don't have too much voltage, too much over voltage experienced by your towers is to improve the ground resistance of the tower itself, meaning that you can reduce the value of this R of tower, and this will directly reduce the over voltage experienced by the tower when it gets hit by a lightning. Another category of transient is when we have a direct stroke on the line conductors. Now, obviously, similar to before, when you have a direct stroke on the conductor, that means that current pulse will be injected into the system and will start moving along the phase conductors. First of all, what's going to happen is if, for example, you have these phases A and B, and if you have this current pulse injected into phase A, it will generate over voltages, and if the voltage between phase A and phase B increases so much that exceeds the breakdown strength of the air in between, you might have a flashover between the two phases, leading to a line-to-line fault. Another possibility, even if you don't have the flashover, is that let's say this is my insulator for phase A. So if you have this traveling wave moving along conductor for phase A, the moment it reaches this tower and the insulator for phase A, maybe the over voltage, meaning that the voltage that is induced here minus the ground voltage at this point might actually be too high for the insulator to be able to tolerate that. So it might cause a flashover leading to a single line to ground fault. So these are the different possibilities when lightning directly strikes a phase conductor. A third possibility is for the lightning to not directly hit the tower or the ground wire or phase conductor, but to hit the ground nearby. When that happens, especially if the distance is small, high voltages may be induced in the phase conductor. So that's one problem leading to overvoltages. And the other issue is that it can actually increase the ground potential of the system. And that can lead to serious issues for the system protection as well. The final scenario involves a situation where the lightning actually doesn't hit the ground at all. What happens is you're going to have clouds that are electrically charged over the transmission lines. As a result of that charge accumulation in the cloud, you're going to have opposite charges accumulated on the transmission line and the structures underneath. When there is a lightning stroke inside the cloud, like between the clouds themselves, what happens is the charges in the cloud will suddenly neutralize. When these charges neutralize, there is no other electric field to maintain the charges on the overhead lines. So they will try to neutralize as well, and this creates an immediate transient leading to voltage and current oscillations that will go again along the lines, moving in different directions. So that's the fourth scenario in which a lightning activity, and this time not a lightning from cloud to ground, but from cloud to cloud, can actually lead to transients in power systems. So this was kind of a quick overview of the lightning transient in power systems. These are a series of references that I have used in creation of this video lecture. In the future lectures, we will continue our discussion on transients by going through switching transients, which, as I mentioned, unlike lightning, which is unipolar, switching transients are bipolar, so they go positive and negative.